So this is an intro to some general characteristics of organic and biochemistry. Organic and biochemistry is this chapter in the textbook, and this just gives an overview of some of the first general properties of these molecules. Organic chemistry is the study of living or once living things that contain carbon. Carbon, of course, is a special atom on the periodic table in group 4 right here that has 4 valence electrons. Since it has 4 valence electrons, its electron configuration of 2s2p2 in the valence shell allows it to form 4 bonds almost all the time. These 4 valence electrons almost always hybridize, so they all have the same energy, and then can make bonds of 4 with lots of other structures. One type of carbon compound has 4 single bonds that form off of the carbon. These form a sp3 hybridized molecule with a 109.5 degree bond angle, and usually forms it always forms a tetrahedral shape. In a 3D model, it usually looks like this, where we have carbon and then 3 atoms on the outside. Those are hydrogens. And this would be connected to, well, in the case of the book, another hydrogen. But you can see that 109.5 degree bond angle here. When carbon forms a double bond, then we get one that forms a trigonal planar, 120 degree bond angle. And this is a carbon, and then they show it double bonded to an oxygen. And then there's a hydrogen out here and a hydrogen out here in this book model. And you can notice that this is a trigonal planar sp2 hybridized shape. And if you forgot what these little shape diagrams look like, this is called a perspective drawing, and it lets us see 3-dimensionally, just like a model right here, what's happening on paper. And so just to zoom in here, you can see that this is what the perspective drawing type shows, that if there is a bond coming out of the paper at you, it's a wedge. If it's little dashes that go into the paper, that means that the hydrogen is behind. You can see here's a molecule we just looked at called methane, and you can see that the carbon and these 2 hydrogens are in the same plane of the paper, and then here the wedge is coming out and the dash is going back in. So if you want to make a note of that right here, you can say that this is coming out of the paper at you, and this one is behind the paper, and these 2 right here are in the same plane as the paper. And so if I were holding this molecule right here, or this part of a molecule right here, I could hold it this way, and you can see that this, if it had a hydrogen on it, would be this hydrogen, and it would be in the same plane as this hydrogen. This hydrogen is coming out at you, and this hydrogen is going back into the paper. And we use this kind of perspective drawing to show the 3-dimensional characteristics of lots of the carbon-containing compounds. Lastly, if there's 1 single bond and 1 triple bond, then we have a linear sp hybridized relationship. So if we had a carbon here with hydrogen going back into the paper, a hydrogen coming out of the paper right here, and then we had a hydrogen in the plane of the paper right here, just like we have right here, a single bond to a carbon, and then there's a triple bond to a nitrogen, then this, of course, would be a 180 degree bond angle, and it would be a linear shape. Let's take a look at a organic substance called ethanol, and let's look at some of its characteristics and how it describes what carbon lots of times does. So here is the molecule called ethanol, just drawn in a stick model, where we have 2 carbons and then an OH group attached to it, making it be what's called an alcohol. Go ahead and pause the video if you need to draw this down. And carbon ends up loving to bond to itself, and you can see that it forms a chain of carbon to carbon right here. And we'll see much longer chains of this as we go through the unit or the chapter as well. They're very stable. The carbon-hydrogen bond is mostly nonpolar, And if you forgot what polar means that they have similar electronegativities. And if you still forgot what that means, here's the trend of electronegativity on the periodic table. If you remember, fluorine is the most electronegative atom. And if you look, carbon and hydrogen are pretty close to one another, 2 and 2.1. And so when they form lots of bonds around one another, like as in this bond right here is not very polar. And it ends up being a nonpolar molecule usually when there's lots of carbons and hydrogens, just because they're close to each other in terms of electronegativity and because they're very symmetrical with one another. Now, in the terms of the alcohol here, you can see that the bond between carbon and oxygen would be very polar. If you forgot the electronegativities here again, you can see oxygen is 3.5, whereas carbon is 2.5. So we have a larger difference in the EL. And then the bond between the oxygen and the hydrogen would also be very polar. And therefore, lots of reactions take place at these places where there's a strong difference in electronegativity and therefore a difference in polarity. These areas, this OH area, is called a functional group. And we'll look at several different functional groups throughout this chapter. You can see glucose molecule right here, the red ones are oxygens, has lots of OHs attached to it. And this allows it to be really soluble in water, because obviously like dissolves like, and water has lots of OHs that are very polar, and so does this form of glucose. Same thing right here with ascorbic acid, which is also known as vitamin C. It's very soluble in water because it's got lots of these OHs and differences in polarity. Whereas something like this substance called stearate, it has lots of chains right here of carbons and hydrogens that are non-polar, and then only one little part right here that would have an OH substituent group to it. So continuing on with this, how do we know if something that's an organic molecule is very soluble? Well, if you remember back from chapter 13, solubility said that like dissolves like. And since these CH bonds in a long chain like this are mostly nonpolar, they're not soluble in water. But if something has an OH like this, like I showed you in ascorbic acid or glucose, or like we had in this alcohol right here on the last page, then it's possible for it to dissolve in water. And so we'd have this attraction right here called a hydrogen bond between the hydrogen bonded to an O and then a hydrogen bonded to an O, or an O with unshared pair of electrons here, and able to form that connection. So look for those types of functional groups when you're looking at molecules that are organic, because that's what makes them either soluble or insoluble in water. So let's look at a couple of groups that you already know. First of all, you've heard of these ones called organic acids, sometimes called carboxylic acids. These have a C double bond OH connected to some chain of carbons. I'll put an R here where the R represents a chain of carbons. Could be one carbon with some hydrogens, or it could be 15 carbons with some hydrogens. Anyway, we use that R lots of times to represent that. And so if it's got a C double bond OH in it, then it's probably got a good chance to be polar and soluble in water, at least in this part of the molecule, because we can see it's got this OH right here. So this is called a substituent group, or a functional group for organic chemistry. Now that's acids. The other one that you've already learned before are ones that make it bases. And these groups are called amines. And amines are ones that have an N with an H or two connected to it, one H connected to it, or just a couple of other representative groups connected to it. Remember, R represents an organic group of C's and H's. These ones with nitrogens attached to them, and these are supposed to be unshared pairs of electrons right here. Unshared pairs of electrons, unshared pairs of electrons, are the basic groups, or ones that would accept a proton. Remember, in acidic groups, the hydrogen right here is the thing that's donated to someone else, and that's the one that's given away, and then we have a little resonance going on here between this double bond and single bond. In the base group, since it has this unshared pair of electrons, it's pretty good at accepting hydrogens right here, being a hydrogen or a proton acceptor. These are usually based off of a compound that's not organic that's called ammonia. Ammonia, NH3, has an unshared pair of electrons right here that is really good at accepting hydrogens. Now you can take one or more of the hydrogens off, and then you can connect some carbon groups. This carbon group happens to have one carbon in it, and as you already know, there are prefixes that allow you to name the carbon groups, and if you only have one carbon in a group, it has the prefix meth. If you forgot your carbon organic prefixes, they're right here. You can see with one carbon, it's a methyl group, 2-ethyl, 3-propyl, 4-butyl. If you forgot those, please take a moment and pause the video and go and highlight that right now so you remember what the organic prefixes are. This would be the methyl group then. We'd have 1, 2, 3 hydrogens coming off of a carbon, and that would be the substituent group that sticks off of the nitrogen right here. Actually, the nitrogen would be the substituent group coming off of the carbon. But this would be the base form right here of the methyl connected to the amine group in H2. Well, let's look just a little bit more at hydrocarbons, ones that have hydrogen and carbon in them. Ones that have hydrogen and carbon in them are of many different kinds. The first ones are called alkanes, and alkanes have carbon-carbon single bonds in them. Then there are alkenes. These are ones that have double bonds in them. So alkanes right here, single bonds between them. Alkenes, these have a double bond between the carbons, at least one or more double bonds. And then there are ones that are called alkynes, and these have a triple bond in them, and they have a Y-N-E ending. There are also ones that are called aromatics, and aromatics are ones that have a cyclic or circle structure to them, or a ring structure. And the most popular one that you learned back in chapter 8 and 9, is called benzene, C6H6, and you can see that it has these rotating double bonds right here that actually end up resonating. And when we learned this, we learned a shortcut way to draw this. Instead of having all the carbons and then rotating the double bonds or showing that the double bonds rotate from one place to another, we just drew this as a hexagon, and then we put a little circle in the center of it. And we said, you're a chemist, you know that there are hydrogens coming off of each one of these, and then each hydrogen is saturated with the number of bonds, I mean 4 bonds, because that's what hydrogen forms, at each corner. And each line represents a bond, and then the circle right here just tells us that the double bond is rotating or resonating. These are characterized by delocalized electrons with resonance. So let's take a look at one hydrocarbon and how we build it or represent it. Here's a hydrocarbon that has 1, 2, 3, 4 carbons in it. And remember, you use prefixes meth, eth, prop, but, pent, hex to name them. And then if it has only single bonds, the ending for that would be ane. And so this has 1, 2, 3, 4 carbons in it. And the 4 carbons would make it have a name prefix but, and then we'd put the ending ane on it. So we'd call this butane. In class, we'll have you build this model. It ends up looking like this. And you can see that it's got 1, 2, 3, 4 carbons in a row. And this carbon right here has 3 hydrogens around it. And you can see those 109-degree bond angles here. Single bonds between the carbons. These carbons only have 2 hydrogens on them, so we'd say this is a CH2 group right here. And then over here, this would be another CH3 group just like this. And you'll notice that it actually kind of has an angular, like it goes back and forth a little bit, and it's not completely straight like we draw it on paper in 3 dimensions. And that's because of the bond angles. That's because of the 109-degree bond angles. And so you can rotate this any way you want on the end, and it's still exactly the same molecule. Same with this one. Now you could rotate it in the middle here too, and eventually you'd have a problem, because if you notice, these two hydrogens right here would come really close together. And of course, since there'd be electrons there, they'd repel each other. And so this formation of butane doesn't happen very often. It usually sits like this, so then all those electrons can spread out and be as far away from each other as possible. This is called a straight chain hydrocarbon, even though it's not exactly straight. And sometimes we'll draw the straight chain hydrocarbons in a shortcut way, where we have 1, 2, 3, 4 carbons, just as lines. And at the end of each line, 1, 2, 3, 4, we know that there's a carbon that's saturated with hydrogens. There'd be 3 hydrogens off of this one, 2 off of here, 2 off of here, and then 3 off of here. Now, if there are branches off of a longest chain of carbon, then it's called a branched chain hydrocarbon. And branched chain hydrocarbons occur when you take a molecule like this, break the bonds, and then we reconnect them, so the molecule still has 4 carbons, but they're not all in the same straight chain. So here would be a molecule that still has 1, 2, 3, 4 carbons in it, but the longest chain would actually only be 3, no matter which way I count it. These branched chain hydrocarbons are called isomers of one another. Isomers. And so butane right here has an isomer that looks like this, carbon to carbon to carbon, and then there's a carbon off of the central atom right here. And this, of course, would have 3 hydrogens around it. This one would as well, and this one would as well. And then this one with only 3 bonds would only have 1 other hydrogen off of it in the center. In class, we'll build several of these today, and we'll talk about how to name these. Because this, of course, is called butane, but this is a derivative or isomer of butane, and we'd actually name it from its longest chain, which would be 3 carbons in a row, 1, 2, 3, or 1, 2, 3, or 1, 2, 3. And so it would actually be called propane, but we'd have a methyl group or a carbon coming off of the second one right here, and so we'd call it 2-methyl propane. So 3 in a row for propane, and we'd say that off of the second carbon comes a methyl group. More on that in class. The nomenclature or naming of a carbon change group like this that has breaks in it or changes in it is called nomenclature. And there are 5 steps to naming these branched hydrocarbons. And I'm going to go through the 5 steps really quickly, and then in class we'll do lots of examples for these. So the first step is to find the longest chain in the hydrocarbon. Find the longest chain. The second step in doing this is to number the carbon atoms beginning with the end nearest a substituent group. So for example, this one in your textbook right here, the longest chain is 1, 2, 3, 4, 5, 6, because there's a substituent group right here called methyl that's coming off of the second carbon. And even though it looks like it goes around in a corner like this, you can still see that they're connected. Now you could have numbered it 1, 2, 3, 4, 5, 6, but then you wouldn't have given the substituent group the lowest number. You would have given it the number 5 instead of 1, 2, 3, 4, 5, 6. So you want to number it so that group that comes off of the chain has the lowest possible number. In our example, we didn't really have a lot of choice. 1, 2, it has to come off the 2. 1, 2, it has to come off the 2. Thirdly, name the substituent alkyl group. Therefore, you put a YL at the end, just like I called this a methyl group. This is a methyl group right here. And then begin with the name and number of carbon that it's attached to. So this one would be called 2-methyl because this group right here comes off of the second carbon. This would be called 2-methyl and then propane because the second carbon has a methyl group coming off of it. And then if there's more than two or more groups attached to it, you alphabetically name them. Here's one more example. This one, kind of tricky to find the longest chain. 1, 2, 3, 4, 5, 6, 7. And then you can see off of the second group is a methyl group. Off of the third group right here, or third carbon, there's an ethyl group. And then here we have a methyl group coming off of 4. And here we have a methyl group coming off of 5. And so this one, alphabetically, we've called 3-ethyl, because off of the third group comes an ethyl group. And then 2, 4, 5, trimethyl, because there's 1, 2, 3 methyl groups, one off of 2, one off of 4, one off of 5. And then we name the longest chain. And the longest chain of 7, of course, is called heptane. Here are some condensed structural formula common group names. Methyl for one carbon, ethyl, propyl, butyl. This is another one, isopropyl, and this is called tert-butyl as well. We'll do a lot of practicing of this naming and nomenclature in class, and then you'll be able to not only name them, but build the models and say a little bit about their polarity and a little bit about their solubility and a little bit about the substituent groups that are attached. Best of luck with your intro to organic.